This is Tim O'Brien coming to you from Seattle in November of 2025. And this is part one of a series on databases and the emergence of vector databases. The information I'm sharing is up to date as of November 2025. And in an area that's this active, things are bound to change fast. And today I want to highlight a story that I published on Medium back on September 7th, 2025. It's about the questions I ask in technical interviews to gauge someone's real understanding of databases. I like to open with a curveball. Have you ever been humbled by a relational database schema that you created? It's not a trick question. I'm not trying to sound like a smug old-timer who remembers the real internet. I'm trying to see whether you've had that moment when a database that you created pushed back and said no. And if that question makes you lean back and say, oh, I've got some stories, then that's the signal. Because anyone who has shipped a database to production has a story, and they have a story that involves them failing. And that's actually what I'm after. I'm trying to find evidence that you've been humbled by a database. And yes, I know I'm starting to sound like Quint. Quint is that character in Jaws. He was the grizzled, old, experienced shark hunter that shows up in the town meeting. He has stories about dangers lurking, and he says, you all don't know what you're doing. And that's how I feel after more than several decades of working with databases. Databases will always win. They're hard to catch. And you really have to know what you're doing if you're using one. And so in today's episode, I'm going to talk about the landscape around databases, how the staffing has changed, how the types of databases have changed. And this is actually part one of a 5-part series on the evolving world of databases. In this part, we're going to focus on the changing landscape. And then we're going to start developing some of the ideas that are around vector databases. So part 2 focuses on vector databases. What are the terms that are involved with vector databases? How do they work? In part 3, I'm going to explore the landscape. Who are the contenders? Because there's an overwhelming array of options that are out there. There's even some existing databases that are trying to slap vector storage into their current feature set. In part 4, I'm going to bring it back to a larger topic, which is databases as a whole. I'm going to propose some North Star rules that'll guide your database decisions in an increasingly complex landscape. And then in the last part of this series, we're going to take those North Star principles and apply them specifically to vector databases. Before we jump into this series, I want to make it clear who is the target audience for this. I'm developing this content for working professionals, people who are using technology, but I want to identify that parts 1, parts 2, and parts 4 are going to be more general. I'm going to go out of my way to explain some of the concepts that I'm using. Part 3 and part 5 are highly technical as we dive into the meaning of some of these vector database concepts and some of the practice. Those 2 episodes are going to be more technical. So if you're not a programmer or if you're not a database administrator, you can probably skip parts 3 and parts 5. But if you're just wondering what is a vector database and how does it relate to generative AI, this episode and part 2 are going to be valuable to you. So let's jump into the last 30 years in the database space, and I want to talk about what has changed. So we're going to start with a story about some ancient database wisdom. I want to talk about how did we used to use databases. So back in 1999, I worked at one of the biggest financial websites of the .com era. 60,000 paying subscribers felt massive then. And this was before smartphones. This was before we were using words like viral and memes. This was before the continuous deployment or the DevOps movement happened. When I went to see The Matrix when it came out in a movie theater, I had a Motorola flip phone and a beeper. I also had a Palm Pilot. So that was cutting edge. Web pages were static hypertext markup language, and that was still new. JavaScript was optional. And if the site went down, we'd gather around beige monitors, cathode ray tube monitors, watching logs scroll by. At the center of all of these websites was a massive Oracle database. It was running on a Solaris box, and guarding that database was our database administrator. Now, where I worked, he was named Albert. Albert was Russian. Someone mentioned that he might have worked in a nuclear reactor control system at one point, and it fit his demeanor perfectly. He typed with 2 fingers, carefully and deliberately, as if each structured query language command carried moral weight. Albert knew everything about the Oracle instance, every table, every index, every nuance of its temperament. And developers like me, we weren't on the front lines of database work. We went through Albert. And we were fine with this. No one wanted to upset the Oracle database. Need a schema change? Walk to his desk and talk to him. I needed to add some indexes to a table because I thought that would speed things up. And he quietly looked at me and said, "Indexes slow down inserts." And he'd warned me in his measured way, trying to dissuade me from this idea. The Oracle database was his reactor core, and he was the one keeping it from melting down. Then came the day I thought I knew better. We were launching a portfolio tracker to be announced on our TV show, and I was convinced it needed to have a new index for performance. Albert continued to be skeptical, but quiet. He tried patiently to dissuade me, explaining why it was a bad idea, but I was young and exceptionally overconfident, certain that I could optimize better than this slow-typing gatekeeper. I mean, what is a DBA anyway? I persisted, and finally he relented. "Okay, give me 30 minutes. I will try." Within minutes of going live, the site slowed to a complete crawl. Writes backed up, queues exploded, and the impatient newsroom people were getting angry. Albert didn't say, "I told you so." He just shook his head slowly and began typing, 2 fingers at a time, fixing what I had broken. And that was the day I learned that databases don't forgive your arrogance. They'll wait patiently for it to reveal itself in production and fail at the least convenient time. I tell this story because it was my first real lesson in database humility, but it certainly wouldn't be my last. Over the next 25 years, I was humbled by databases in countless ways, by replication lags that broke real-time features, by missing indexes that brought production to its knees, and by schemas that couldn't scale with the business. But what changed dramatically since that day that Albert isn't just the technology, it's our entire relationship with databases. These gatekeepers, these DBAs, have largely disappeared, and with them went both the frustration of having to go through these intermediaries, plus the wisdom that prevented some disasters. Understanding how we got here and what we lost along the way, that's crucial to avoiding the next generation of database disasters. So to go back to the original thought, when I'm interviewing someone now, 2.5 decades later, I'm trying to find out if they have had a similar experience with databases, if they have learned from databases and understand that this is one of the most nuanced and difficult topics in IT. So what changed, and why is Albert, or a DBA, harder to find in 2025? 2 decades later, 2.5 decades later, the way that we build and run databases is radically different. First, we've had an explosion of database choices. There are dramatically more databases to choose from. When DB Engines launched its ranking in 2012, it tracked 28 systems. By 2015, it covered 256, and by 2016, it was 303. This month, it lists 426 different databases, and this is from DB Engines. And that explosion mirrors the web's scale problems over time and the NoSQL wave that was kicked off by systems like Google's Bigtable in 2006 and Amazon's Dynamo in 2007. And those were 2 innovations that really normalized trading ACID, atomicity, consistency, isolation, and durability. These are things you would get in a relational database for web scale availability and throughput. And we needed this. We needed this because our websites, our largest systems, were scaling from tens of thousands and hundreds of thousands of users up to billions of users. But it's not just about quantity. The types of databases have fundamentally changed. According to DB Engine's popularity rankings, as of November 2025, Oracle, MySQL, and Microsoft SQL Server still dominate the top 3 spots. These are the relational database stalwarts. But look at positions 4 through 10. Postgres, MongoDB, Redis, Snowflake, Elasticsearch, Databricks, and IBM DB2. Now, some of those are other relational databases that are open source, but Redis is a key value cache. MongoDB is a doc store. Snowflake is a cloud data platform. Elasticsearch is a search engine. And that top 20 list includes even more types of databases. There's a graph database called Neo4j. There's Cassandra. There's a time series database called InfluxDB. And there's multimodal systems like DynamoDB and CosmosDB. Stack Overflow's 2023 developer survey tells a similar story. Postgres is now the most popular database among professional developers, greater than 50%, followed by MySQL, SQLite, MongoDB, Microsoft SQL Server, and Redis. That diversity is striking. Developers aren't just using, quote, a database. They're orchestrating specialized systems for specific workloads. And I learned this the hard way. In 1999, my applications were simple. A web server talking to an application server, talking to Oracle, period. That was it. Today, my last production system, it revolves around a Postgres database for transactional relational data, but also uses Redis for session caching, Elasticsearch for full-text search, GCS for object storage, Firestore for document storage and NoSQL storage, and thanks to AI, it's using Pinecone for vector embeddings. And each technology decision made sense. We evolved to this place where a highly scalable application has to make use of several different database technologies at the same time. And that complexity makes it less likely that you're going to have a DBA. You're going to have one person sitting there that's in control of the schema of all the operations. To understand how we went from everybody uses Oracle or MySQL to today's overwhelming menu of database options, I think it also makes sense to trace the key moments that drove this evolution. And it's a story of web scale, breaking traditional assumptions, and engineers repeatedly solving the same problem. What happens when your data doesn't fit in one box anymore? And one of the motivations for me recording this episode is also to capture this history. I work with a lot of people who were not paying attention in 2004 because they might have been 10 years old. They weren't focused on the NoSQL revolution. They weren't there. And when I talk about this history, I also want you to understand the word history is strange. This isn't 60 years ago or 70 years ago. This was less than 20 years ago. So the first cracks in relational databases monopoly on applications appeared when Google published their big table paper in November of 2006 at OSDI, Operating System Design and Implementation. The paper was authored by Fei Chang and colleagues, and it described a distributed storage system for managing structured data that is designed to scale to a very large size, petabytes of data across thousands of commodity servers. This wasn't just academic theory. Bigtable was already powering over 60 Google products, including web indexing, Google Earth, and Google Finance. And the key insight in the Bigtable paper was radical for its time. You could sacrifice some ACID guarantees in exchange for massive scalability and availability. As the paper noted, Bigtable does not support a full relational data model. Instead, it provides clients with a simple data model that supports dynamic control over data layout and format. This trade-off would echo through the next decade of database design. Amazon followed with their Dynamo paper at SOSP, Symposium on Operating Systems Principles, in 2007. They were introducing the concept of eventual consistency, another heretical idea in the world of traditional databases. These papers didn't just describe systems, they gave permission to the entire industry to think differently about data storage and horizontal scale. So that's when Facebook showed up. Remember, Facebook was still very new, but in 2007, the number of users they were supporting was growing astronomically, and they needed a way to do inbox search. So the first major open source fruit of this NoSQL revolution was Apache Cassandra. It was developed at Facebook in 2007 by Avinash Lakshman, who was coincidentally one of the Dynamo paper authors from earlier that year, and Prashant Malik. Cassandra was built to power Facebook's inbox search feature, and this was a problem that required storing massive amounts of data with high write throughput and availability across multiple data centers. Facebook open-sourced Cassandra in July of 2008 and became an Apache incubator project in March of 2009. By February of 2010, it had graduated to a top-level Apache project. Cassandra combined Bigtable's data model with Dynamo's distributed architecture, creating what would become the template for a new generation of wide column stores. As Lakshman described it, Cassandra was designed to fulfill the storage needs of the inbox search problem and handle billions of writes per day. Around the same time, while Google and Facebook were solving scale problems with distributed systems, Emil Eifram was tackling a different challenge. What happens when the relationships between data points are as important as the data itself? In 2000, during a flight to Mumbai, Eifram sketched the initial design for a property graph model on a napkin. He was frustrated with how poorly relational databases handled connected data, the very thing they were supposedly designed for with their relational model. The problem was real. Try modeling a social network, a fraud detection system, or a recommendation engine in a traditional relational database, and you will quickly hit a wall of complex joins. As data relationships grew deeper, query performance degraded exponentially. 6 degrees of separation might be a social phenomena, but in a relational database, it's a query that might never return. Eifram, along with Johan Svensson and Peter Neubauer, spent the next 7 years building Neo4j, which they officially launched in 2007. Neo4j treated relationships as first-class citizens, storing them directly alongside the data. A friend connection wasn't a foreign key in a junction table, it was an actual traversable edge in a graph. So NoSQL, graph databases, what was next? Parallel to the NoSQL movement, another evolution was happening. Caching systems were becoming sophisticated enough to serve as primary data stores. Brad Fitzpatrick created Memcached in 2003 for LiveJournal. It was initially just a way to cache database query results, but as web applications demanded faster response times, developers began using Memcached for more than just caching. They would use it for session storage, counters, and even as a primary store for ephemeral data. Then, in 2009, Salvatore Sanfilippo released Redis, which he described as a data structures server. Redis blurred the lines completely. Was it a cache? Was it a database? Was it both? It supported persistence to disk, replication, and complex data types like sorted sets and lists. As Sanfilippo explained in early documentation, Redis is not a plain key value store. Actually, it's a data structures server, supporting different kinds of values. But this evolution reflected a broader trend. As web applications became more complex, the boundaries between different types of data storage began to dissolve. The question was no longer cache or database, it was what's the right tool for this specific data access pattern. So this explosion of unstructured data, logs, documents, user-generated content, created another category entirely, search databases. Apache Solr had been around since 2006, but Solr Cloud was introduced in 2012, and it transformed into a distributed search platform that could rival traditional databases for certain workloads. Elasticsearch was released in 2010 by Shay Banon, and it took this idea even further. Originally built to help his wife search recipes, Elasticsearch became the foundation for log analytics. It also proved that search engines could serve as primary data stores. As Banon noted, Elasticsearch is not just about search. It's about making massive amounts of data usable in real time. Now, perhaps the most radical expansion of the database definition came from messaging systems. Apache Kafka, released by LinkedIn in 2011, started as a messaging queue but evolved into something much more profound. It's a distributed commit log that can serve as a source of truth for entire architectures. Jay Krebs, one of Kafka's creators, argued in his 2013 article, The Log, What Every Software Engineer Should Know About Real-Time Data's Unifying Abstraction, that the log itself could be a database. The log is the record of what happened, and each table or index is a projection of this history into some useful data structure or index. This thinking led to architectures where Kafka wasn't just moving data between databases, it was the system of record. While I haven't included messaging and queuing systems in this series, things like Kafka, RabbitMQ, Amazon SQS, their evolution shows how the boundaries of what we consider a database have expanded. Modern architectures often use these systems not just for messaging, but as durable stores for event sourcing, effectively making them part of the broader data landscape. So what drove this expansion? The numbers tell the story. In 2004, Facebook had 1 million users. By 2008, it had 100 million users. And by 2012, it had 1 billion users. Google was processing 20 petabytes of data per day in 2008. Twitter went from 5,000 tweets per day in 2007 to 110 million per day by early 2011. Traditional relational databases designed for consistency and transactions simply could not handle this scale without a lot of fail whale moments on Twitter. But it wasn't just about scale. It was about the nature of the data and access patterns. Social graphs needed flexible schemas, graph databases. Time series data from IoT devices needed time series databases. Session data that needed microsecond access times, key value stores. Log data that needed extended full-text search across billions of entries, search engines. Streaming data that needed to be processed in real time, stream processing platforms. As Werner Vogels, CTO of Amazon, put it in 2018, developers are no longer using a single database for all use cases. Purpose-built databases. That's what were needed for different workloads. This wasn't a failure of relational databases. It was a recognition that no single system could optimize for all use cases. And in the span of a single decade, we went from a relational monoculture of the late 1990s, where choosing a database meant picking between Oracle, SQL Server, or MySQL, to today's landscape, where DB Engines tracks 426 different systems. Each of those new systems solved a real problem, but collectively, they created a new problem. Well, how do you choose? How do you train your team? How do you avoid building a Rube Goldberg machine of interconnected nonsense? How do you make sure that your developers are choosing the right technologies? So I'll bring it back to what I was talking about at the beginning of this episode. That interview question that I asked. Have you ever been humbled by a database? Given that we have 426 to choose from, almost everybody that works with databases at a certain point in their career has a story. The opportunities to be humbled have multiplied exponentially. And without an Albert or a DBA looking over your shoulder, you're going to learn these lessons the hard way. But there's another reason why we don't have DBAs, and it's related to the cloud. The cloud was the great democratizing influence of technology. And one of the reasons they created the cloud was to get rid of intermediaries. Developers should be able to have direct access to technologies. They should be able to spin up a database and get started. Go back to 1999, if you needed a new testing or production database, it might take weeks. It took a lot of time. I remember having to install Oracle on my IBM ThinkPad in 1999, and it was like, I think we still had CD-ROM drives, not even DVDs. It was like a stack of 10 of them. It took maybe 2 days. And compare that to right now. If I wanted a new relational database right now, I could go into Google Cloud Console. 5 minutes later, I'd have a relational database running to the specifications that I wanted. It could be multi-region. Backups would be configured to Google Cloud Storage. That didn't exist in 1999. The only way that we could do it is if we had a DBA. So the cloud changed that DBA calculus. Gartner has been saying this for years. By 2019, they projected 75% of databases would be deployed or migrated to the cloud by 2022. And the cloud database management systems already accounted for most of the market's growth. By 2021, about half of the revenue in databases came from cloud, and by 2022, almost 100% of market growth came from cloud, according to Gartner market share analysis for spend on databases. The financial scale of this shift is staggering. According to Synergy Research Group, global cloud infrastructure services spending hit $270 billion in 2023, up from just $6 billion in 2010. Amazon Web Services alone generated $90.8 billion in revenue in 2023, and this growth will only continue. Gartner projects that cloud spend will grow to over $1 trillion by 2027. So this isn't just moving servers to someone else's data center. It's a fundamental shift in how we were thinking about infrastructure. Right now, if you're working at a company that's using cloud, you're not thinking about servers. You're deploying on AWS RDS. You're using Azure Databases. You're using Cloud SQL on Google. If you're working at a large enough company, yes, you may still have a couple databases running on servers, but for the most part, if you're experiencing a database, it is hosted on the cloud. Automated backups, point-in-time recovery, read replicas, failover, patching, high IOPS storage, all of these tasks that used to require DBAs became checkboxes in a console. The cloud didn't just arrive, it started to get rid of the need for people to have DBAs on staff to worry about operations. Now, the other factor that affected DBAs were the number of languages that people were using and how integrated those languages were with the databases. Teams are more polyglot, and developers own more of that database surface area. In Redgate's 2021 survey, 70% of orgs used more than one database. And about half of the respondents said they use continuous delivery for database changes. And let me explain what that means. If you're writing an application and it's sitting next to a database and you're continuously delivering or integrating changes to your database with what's called a CI/CD system, then it means that you're running migrations. It means that every time you make a software change, your developers are going over to another folder or another project, and they're executing DDL statements that change the schema. That was not something that was occurring in 1999. And that also implies that developers are now more responsible for both the application and the database development. So again, in 2018, Redgate found that 76% of developers were responsible for both, and 58% said the dev teams and the DBAs worked together. So those were not the staffing patterns of 1999. In 1999, we could have implemented the site in Java. Maybe we could have used Perl. That would have been insane. We could have written it in C. There weren't as many languages that were ready or available to write websites. Fast forward a decade, .NET was available. Today, if you look at Stack Overflow's 2023 survey, it shows developers are using JavaScript, TypeScript, Node.js, Python. They're using Java. Some people are using Go, C#. People are using Rust. There's Ruby. Each language also brings its own database libraries. These are called object relational mappers. And there's a lot of passion about whether or not you should use these. But if you're a Python developer using SQL Alchemy, you're going to think differently about database design than a Go developer that's writing raw SQL, or a Node.js developer using Prisma or Sequelize. If you're a Java programmer using Hibernate, you're going to be doing things that don't necessarily require you to talk to a DBA. And I get it, there is some debate over that. Some people are allergic to object relational mappers, but the larger point is, our languages now bring tools with them that help us use the database. That did not exist in 1999. So just to set up where we are, this whole episode is about the changing story of databases and how that affected DBAs. And the real story is told by the labor numbers. So the US Bureau of Labor Statistics counts headcounts for DBAs versus software developers, and it shows it very plainly. In 2000, we had 639,000 software developers. We had 108,000 DBAs. So that ratio is approximately 6-1. Fast forward 18 years to the year 2018, 1.3 million software developers. Database administrators, 110,000. So barely 2,000 more over 18 years. 12-1, so 12 developers per DBA. Now, if you want to look at May 2023, this is where it gets interesting. 1.7 million developers to 76,000 DBAs. Now that's a reduction of about 30,000. And if you really want to drill into database architects, there were only 59,000 of those in May of 2023. So that ratio is between 12 developers and 22 developers for every DBA. So that math is fairly inescapable. The number of developers more than doubled from 2000 to 2023, and the number of DBAs declined by 30%. And this isn't just labor statistics, it's a fundamental shift in how software is built. Today's 12-1 or 22-1 ratio means entire teams ship code without ever talking to a database specialist. The knowledge that used to live in one person's head, indexing strategies, query optimization, capacity planning, that's either moved into the platform or it's been distributed across the team. Developers know more about databases in 2025 for sure, but sometimes it works and sometimes it doesn't. Put simply, the web and the cloud multiplied database choices and made the platform smarter. And in the process, the everyday developer got much closer to production data decisions. And the classic always within arm's reach DBA, like Albert, didn't just move further away. In many cases, they disappeared. And some of those roles have morphed into site reliability engineers, SREs, data engineering roles. There's people that work with cloud that now do similar things. You may have someone looking at disk performance and IOPS. But the thing that we're missing, the thing that has gone away, is that individual who only focuses on databases. They exist. 100% there are still DBAs. There might be a DBA listening to this saying, wait, what's going on? I still do this. This role still exists. My main point is it exists less for some of the development teams that are working in 2025. And later in this series, I'm going to argue that we need to reinvest in this role. It's a new role. It's a more complex role, but we need to hire more people to focus on databases and databases alone. So we've gained speed, we've gained elasticity and choice, but we've lost some of that wisdom, the kind that whispers, don't add that index to the hot write path, or this workload is a perfect fit for a key value store, not a relational schema. We've left that expert that's able to question your developer wisdom. And because of that, the bill for that absence shows up as over-provisioning, bad technology choice, accidental hotspots, and cloud waste, because the wrong database is one of the most common contributors to increased cloud spend. And that brings us to where we are today. We have 426 databases, a 12-to-1 or 22-to-1 developer to DBA ratio, and teams juggling every database they can get their hands on. We've traded Albert's careful oversight for cloud automation and polyglot persistence. And sometimes that trade works, but other times it ends up in a 3 a.m. incident call where none of the developers know what an explain plan is. So I hope you walk away from this episode understanding that the last 25 years in databases has driven some real change. There's more database types available. There's more challenges. There's complex architectures that use 5, 6, 7 different database types. But I think most importantly, and the big takeaway I want you to take from this episode is, it's had a real impact on what we think about when we think about who's here to help us use and manage the database. And the reason I've told you this 25-year story is because we're about to go through another revolution, the emergence of vector databases. These are the databases that help us fine-tune and use generative AI models. And they're showing up so quickly that I'll wager that there's a lot of people out there right now who are realizing that they have to become vector database administrators almost overnight. So I hope I've cheered you up. This is part 1 of a 5-part series. And my podcast is known to make people worry about things. But I want you to know that the next part of this series is going to be more focused on what's new. What are the new things that can break in entirely unexpected ways? I'm going to talk about the new kid on the block, vector databases. And if you thought that the explosion from Oracle-only shops to 426 different database systems was dramatic and confusing, wait until you hear about artificial intelligence and vector databases. Vector databases are purpose-built for something that didn't even exist as a widespread need 5 years ago, storing and searching through high-dimensional mathematical fingerprints that fall out of modern AI models. When OpenAI's text embedding tool converts your paragraph of text into a 1536-dimension vector, or when a vision model turns an image into a 512-dimensional vector, traditional databases simply are not equipped to handle it. B-trees were not designed to find the 10 most semantically similar documents to this query. So in part 2, we're going to drive into this brave new world where meaning itself becomes geometry, where seemingly unrelated concepts can be mathematical neighbors, and where choosing the wrong algorithm can mean the difference between millisecond responses and bringing your entire semantic search system to its knees. In part 2, we're going to explore what vector embeddings really are and why they're revolutionary, how high-dimensional spaces break our intuitions about data, and why approximate nearest neighbor search is both a blessing and a curse. We're going to talk about the fundamental operations that make vector databases different from everything we've discussed today. If you're building anything with AI in 2025, you need to understand vector databases, not just use them. They're not just another database type. They represent a fundamental shift in how we think about storing and retrieving information. So join me for the next episode as we explore why vector databases went from academic curiosity to the critical infrastructure that you're using every day.